For our last lesson in kinetic molecular theory, we are going to talk about intermolecular forces in molecules, how that affects the phase changes, and we are going to focus on vaporization and boiling and talk about boiling points with intermolecular forces. Okay, so here's just a review of our intermolecular forces. Remember, it's between molecules. It's not inside. It's not those bonds inside. It's the attraction. So those molecules are going to click together like magnets. So our first force, and if we're comparing in the same molecule, this would be considered the weakest force, is London dispersion. This is due to the electron motion and the probability that those electrons may clump up for just a moment, creating a temporary dipole. Okay, this is in all substances. However, it is the only intermolecular force in a nonpolar molecule because there would be no poles. So remember, nonpolar molecules, we have a center atom and it's surrounded by exactly the same thing. And so what happens is there's no pull, so the electrons aren't pulled to one side or the other, and it means we have no poles. It's nonpolar. Okay, and I'm just going to draw a little thing off to the side here and show you the difference. So carbon surrounded by 3 H's, but what if one of those H's became a chlorine? Remember, chlorine's very electronegative, so it's going to pull those electrons up here, and then I'm going to have a partial negative charge. That's not a full charge, it's just partial, and a partial positive down here. So now I have a north pole and a south pole, a negative pole, a positive pole. I have poles. So this is my polar molecule. Okay, so a little review on that. All comes back around. And our next force is our dipole-dipole. This is when we have a polar molecule. And here I don't have an even tug of war. Fluorine is the most electronegative atom on our periodic table. And so what does that do? It pulls all the electrons towards it. Electronegative is an electron hog. So that's a partial negative, and this side becomes a partial positive because I still the electrons. And then when it meets up with that same molecule in a cup, we got a positive and a negative attracting each other. And right here, this attraction between molecules is the dipole-dipole attraction, or the intermolecular force between the molecules. Now, hydrogen bonding is that special dipole. It's so special that we don't call it a dipole. We call it hydrogen bonding. It's uniquely strong and it changes the properties of many things. In order to be a hydrogen bond, it must be bonded to a nitrogen, an oxygen, or a fluorine on one molecule, and then it's attracted to a nitrogen, oxygen, or fluorine on another. So here I have 2 molecules with hydrogen bonding. This oxygen is so extremely electronegative, it hogs all the electrons over here, causing that dipole. Fluorine is the most electronegative atom, and it hogs everything here, causing a dipole again, partial positive, partial negative. And here, between the molecules, this attraction, that's what these wiggly lines are. That's my hydrogen bonding, okay? Just to drive that point home, here I have 3 hydrogens bonded to a carbon, and this hydrogen's bonded to an oxygen, okay? So let's say that I have an oxygen bonded to a hydrogen here, and an oxygen bonded to a hydrogen here, and these guys attracted each other, and these guys attracted each other. Frame. There's only one hydrogen bonding site here, and that's this one, because my hydrogen has to be bonded to an oxygen in order to form a hydrogen bond. Okay, so this hydrogen is bonded to a carbon. Yes, it is attracted to this oxygen bonded to a hydrogen, but this is not a hydrogen bond. Okay, the hydrogen has to be the one doing the attraction, and it has to be bonded to an oxygen, a nitrogen, or fluorine, and that's not there. Now, this hydrogen over here is bonded to an oxygen, so it could make a hydrogen bond with something attached to a fluorine, a nitrogen, or an oxygen. So make sure that you understand the difference between hydrogen bonding and just a dipole bonding, okay? This is my hydrogen bond. Okay, so how does this affect our phase change? So we talked about this a little bit already, but we have solids, liquids, and gases. And solids are held together very tightly. They have very low kinetic energy. They're just vibrating, and they have very strong intermolecular forces or high intermolecular forces. Now, if you think about these as tennis balls held together by Velcro, when we're vibrating those tennis balls, the Velcro really doesn't move. Now, if I start wiggling those tennis balls more, you could start hearing the Velcro rip, okay? They won't come apart completely, but that's the intermolecular forces or the attractions between molecules starting to weaken, okay? Which is why these can slip by each other now. And if I start really tugging on those tennis balls, they'll start ripping apart. I have more motion, more kinetic energy, and basically, if they're not touching at all in an ideal world for an ideal gas, we'll say that they have no intermolecular forces. So very strong intermolecular forces, but then my motion, my temperature starts increasing as I go to a gas, and that's going to weaken those attractions between molecules. And that's really why our phases are starting to change. So now we're going to focus on vaporization. And vaporization is two things. It's evaporation and boiling, and they're very different. So we need to know what our vocab words are. First of all, what is atmospheric pressure? Atmospheric pressure is just our atmosphere. It's the force of those air molecules colliding with the surface. They're bouncing off my hand right now. As a matter of fact, if you wave your hand around, you can feel the air bouncing off your hand. And a force is just a push. So when we're talking about gases, we're talking about collisions, billions of collisions of air molecules hitting my hand. Okay? Now, the other thing we need to talk about when we talk about evaporation and boiling is vapor pressure. And this is just the pressure of the molecules above a liquid. So down here, I have some evaporation and we have some particles above this liquid, and those will bump into things. So that's the vapor pressure, the pressure of those molecules above the liquid. Vapor pressure is easy to understand if you just think about 2 cups of water, okay? So here I have a cup and you can see it's perfectly clear. And here I have very hot water. It's actually hurting my hand and you can see all the hot condensation on the side, okay? So if I put my hand over this cup, you might be able to feel a little bit of the vapors hitting your hand above there. But when I get hotter, and you can feel that hitting your hand a lot more. So get a really hot cup of water and a really cold cup of water, and you can feel the vapor pressures increasing. Why? Because more water is escaping here. Okay, so let's look at evaporation versus boiling. So remember, evaporation rate is just, here I have my atmospheric pressure pushing down, and I have some vapors or some water going from liquid to gas escaping because it has enough kinetic energy. This is room temperature, so I have a few particles above the water, but not enough pressure going on here to escape the atmospheric pressure and start going right everything into a gas. Now I have warmer water here. So you can see with warmer water, even more particles can escape. They have enough kinetic energy to escape. So I have more particles above this liquid. More particles hitting me, that is vapor pressure. Okay, so when I warm that up, I have more vapor pressure. So what happens here? Well, when it's cold, I have very high intermolecular forces holding that water together. I have a low kinetic energy, which means I have a low vapor pressure. Okay, as I warm it up, I start weakening those intermolecular forces because I'm increasing my kinetic energy or motion. Remember, kinetic energy is temperature, which means I'm getting more particles above the water. So I'm increasing my vapor pressure. Vapor pressure is the amount of molecules above a liquid. Now that's very different from boiling, okay? So boiling is when my vapor pressure equals atmospheric pressure. And you can see here I made these lines equal. That's vector math, okay? Here I have not very much pressure. I warmed it up. I have more vapor pressure. And here everything's trying to escape into a gas because I have low intermolecular forces due to the high temperature or the high kinetic energy, which causes a very high vapor pressure. so high, this is all going to go into vapor. If you let that boil at 100 degrees C, if you let it boil, it will all boil away. Okay? So let's talk about vapor pressure versus intermolecular forces. And this is going to be between different substances, okay? So strong intermolecular forces keep those particles together. That means we have a less evaporation, which means we have a low vapor pressure, and we have a very high boiling point. Why do we have a high boiling point with low vapor pressure? Because these molecules are held so tightly together that I need more energy to change it to a gas. Okay, so to go from a gas to a liquid, I need a lot of energy if I have strong intermolecular forces. Um, those strong intermolecular forces keep it together, which means I have that low vapor pressure and I need a lot of energy, so I need a high boiling point to make that go into a gas. If I have weak intermolecular forces, the particles come apart very easily, which means I have more evaporation, right? They can break apart and go into a gas, which means I have higher vapor pressure because I have more gas above that liquid. It also means I have a low boiling point. I don't need a lot of energy to rip apart those molecules and go from a liquid to a gas because they come apart very easily. So let's compare our water to our carbon tetrachloride. Now, water has hydrogen bonding, and we said that was very, very strong. Carbon tetrachloride is surrounded, my carbon's surrounded by all the same guys, which means this is nonpolar, okay, which also means that I have London dispersion only, which means I have relatively weak intermolecular forces. So let's compare these at room temperature. At room temperature, my water has very strong intermolecular forces, which means I don't have very much evaporation, okay? Mostly they're staying together. I have a few with enough kinetic energy to escape. So I have a low vapor pressure going on here, and water has a very high boiling point. It boils at 100 degrees C. I need a lot of energy to rip apart these molecules. Carbon tetrachloride, on the other hand, has weak intermolecular forces. It's London dispersion only, which means I have more evaporation, which means I have a high vapor pressure. I have lots more particles above this liquid, and it doesn't take very much energy to boil, so I have a lower boiling point, 70 degrees C. Now, when things evaporate easily, they're called volatile. So carbon tetrachloride is a more volatile liquid than water is. So now we can use intermolecular forces to compare the boiling point vapor pressure of two different liquids. So when we were just talking about carbon tetrachloride has a higher vapor pressure, here's the graph. Here's my temperature. As I increase the temperature, this is vapor pressure. My vapor pressure increases, and you can see carbon tetrachloride already has a higher vapor pressure than water. And we're going to analyze this a little bit more. So our last vocab term would be normal boiling point, okay? What do we mean by normal? We say that water boils at 100 degrees C, okay? So what we mean is the temperature a liquid boils at atmospheric pressure of 760 millimeters of mercury. That's normal boiling point. It boils at basically, this is atmospheric pressure at sea level, okay? Now, atmospheric pressure, we have many different units for pressure. We have millimeters of mercury, which is 760 is our standard, our normal atmospheric pressure, which is also 1 atmosphere, so there's another unit, or 101.3 kilopascals. And we'll talk more about that in our gas units. But what we need to know is what happens if I lower that vapor pressure, because remember, boiling is when atmospheric pressure equals vapor pressure. So here we have our vapor pressure at sea level, 760 millimeters of mercury, and water boils at 100 degrees C, okay? Because remember, it's when these two things are equal, atmospheric pressure equals vapor pressure. So if I lower my atmospheric pressure, that means I can lower my vapor pressure as well, and that means I have a lower boiling point. So if I lower it to 500 millimeters of mercury, it's about 85 degrees C. Now this graph down here is not exactly drawn, but that's pretty close to real life, okay? So when we lower the vapor pressure, we lower the temperature to boil. Okay, so now if I look at a graph like this, I can find the vapor pressure at different temperatures. Okay, so at 60 degrees, my vapor pressure is about 400. Okay, millimeters. Okay, so now if I want to find the normal boiling point of carbon tetrachloride, I figure out this point right here. This point right here, this line is 760, and that is my normal boiling point pressure. So I just look over here, okay, where it hits the graph, and I come on down, and my normal boiling point for carbon tetrachloride is going to be roughly, let's call that, it's 77 degrees C. Okay. And then for water at 760, it's going to be 100 degrees C. So again, I have this lower vapor pressure, which causes me to have a higher temperature to make it go into gas. Now, if I want to find the boiling point at 400 millimeters of mercury, I just go over to my 400 line and then I go down, and this is roughly a boiling point at 400 millimeters of mercury is roughly 60 degrees C. Why? Because my vapor pressure would equal my atmospheric pressure, and I said that my atmospheric pressure was going to be at 400 millimeters of mercury. Okay, so we will be practicing that.